All right. Hello, I'm going to just jump right in. So obviously we're interested in the 3 micron absorption feature to investigate water and hydroxyl on the surface of the moon. However, interpretation of those results depends on separating reflected sunlight from thermal emission at 3 microns. And there is disagreement over the thermal removal by experts. There's at least 3 different methods for correction in moon mineralogy mapper data. And these can cause conflicting predictions for the behavior of hydration on the lunar surface. So for example, the graph on the right shows the 3 micron feature changing with solar incidence in one thermal correction of moon mineralogy mapper data, and then the band acting differently in a different version. So to approach this, our group uses the NASA Infrared Telescope facility on Mauna Kea to take ground-based telescope observations. So we look between 1.6 and 4 microns. So that goes past the 3 micron cutoff of moon mineralogy mapper data to longer, more thermally dominated wavelengths, which helps constrain our thermal correction. We're able to use it as an imaging spectrometer and make hyperspectral maps. And we also can take advantage of unique observing opportunities. For example, exploiting the changing temperature and illumination conditions due to partial eclipse. So there was a partial eclipse on November 30th of 2020. And this was one day before Chang'e 5 landed. So we took a look at the site before they landed, and we took 5 different observations ranging from 100% solar flux, and then entering the eclipse at 95%, 65%, and then 45% solar flux. And the 45% illumination was the maximum level of eclipse that area experienced. And then coming out of eclipse, we got another observation at 60% illumination. So what's interesting about partial eclipse is that we can, the temperature is reduced because the solar flux is reduced. So the thermal contamination at 3 microns is reduced, letting us sidestep some of this thermal issue. So if you look at the graph in the top right, under full illumination conditions, without correcting for thermal excess, there's a large drop between that and then 50% illumination. And then if you go as low as 25% at 3 microns, you almost don't even need a correction. So we still had to perform a thermal correction, but our results for lower illumination conditions were much less dependent on that thermal correction. So looking at the Chang'e 5 site, here's some spectra from those 5 different observing conditions. So on the top is 100% illumination, and that does not show an apparent band. The 3 micron data is in line with the upward slope of the spectrum or the continuum of the spectrum. But as you go down looking at 95%, 65%, and then 45% illumination, you can see a systematic decrease in the reflectance at 3 microns and the development of a band. And then the 60% illumination exiting the eclipse stays at the level of the 45% illumination band. So we took the 100% illumination case to be 0 water, and we used that to measure the hydration band from using the methods of Lee and Milliken 2017 and Honeyball et al. 2020. So this is a map of the hydration in the area around and at the Chang'e 5 landing site. We used the 45% illumination data set to show the most hydration that we measured. So we can see that the mare shows hydration, and then there's two lighter areas along the top, and those are both correlated with craters on the surface. So if we take, so we were curious to see if the behavior at the Chang'e site was representative of the entire map. So these are the average hydration for the whole map across those observations. So we can see, so this is plotted against time, so you can see how it developed as the eclipse developed. And I've noted the illumination and the temperature along with it for your reference. So we can see as the eclipse progresses, an increase in the hydration measured until we reach 45% flux, which was the deepest level of eclipse. And then exiting, we once again see that the 60% flux stays at that higher level near the 45%, which is interesting because if it was purely due to illumination or by extent temperature, it should be coming down closer to the 65% illumination condition. So to kind of bring it all together, the full illumination results are pretty consistent with other measurements. The Chang'e 5 lander took measurements at the site. Moon mineralogy mapper observations from Leah and Millikan 2017, and our own IRTF observations of similar lunar time of day and latitude. So that makes sense. What is unexpected is the emergence of a 3 micron band during the eclipse. The band that we measured at 45% illumination was about a 4% band. So that's a pretty significant development throughout the eclipse. So we have a few hypotheses for why this is happening. One is thermal infill, and that's just that perhaps we are not fully correcting the thermal effects out of the band. And then that would be temperature dependent. So that could explain the sort of linear temperature dependence we were seeing in that plot. But that doesn't explain the behavior of the 60% illumination condition. The other is the formation of metastable hydroxyl as the temperatures fall. However, these observations were taken in the magnetotail. So our thought when we were first looking at this was that that would mean there wouldn't really be solar wind protons available to form this metastable hydroxyl, but maybe things are changing with the data that Chang'e showed today. And then the other idea is migrating water along the surface. However, the amount that we're seeing form is pretty high compared to, like Paul was saying, the amount of water available in the exosphere from LADI. So none of those quite satisfied us as an explanation. The asymmetry between the onset and the offset of eclipse does offer a little bit of constraint. It would argue against an instantaneous optical process like the thermal infill. And it would argue for a physical process that has some lag behind the changes in illumination and temperature, which if you're forming hydroxyl or acquiring transported water, there might be a lag as temperatures go up before it leaves the surface. So for future work, we collected data during that same eclipse from Sinus Astum, Aries Swirl, and Taurus Littrow, and we are working on reducing all of that data. And there's also another eclipse in November that we have time on. So we're going to design a test specifically to look at that hydration change and asymmetry. And I am open for questions. Thank you.
Question? Yes, quick question. Do you have anybody online?
There's no one currently online who has asked a question to the speaker.
Please come up to the podium. And then go ahead and introduce them.
Hi, Parthi Prem, APL. Oh, I see why Carly didn't lower the mic. Yeah, good talk, Abby.
Thank you.
So, quick question. Did you happen to get observations after the eclipse so that you could see when the band depth came down?
So I think we do have one more observation that isn't currently reduced, that's in full illumination. But we really didn't design this to test a changing hydration band. We were kind of just expecting to just get better noise on one measurement. So I think that we'll have a much clearer picture from the next eclipse.
Cool, thanks.
Yeah, thanks.